Welcome to this video on theoretical and experimental probability. Throughout this video, I'm going to show you how to calculate those two different types of probabilities. But before we get to doing that, we got to look at a little vocabulary. And this first one is one of those probabilities. It's based on known characteristics or facts. It kind of tells you what should happen. All right? And that's the theoretical probability. So what should happen if I run this experiment? Not necessarily going to happen, but it's theoretically this is what will happen. So I like to think of it in terms of some different things that we're familiar with. And my first one is dealing with a coin. If I take my coin and I flip it, I want to know what's the probability that ends up heads. Well, the way I like to think of it is I like to go back to my sample space. And what is my sample space? Well, I have given you the sample space here and here. If I flip it, I could end up with a head, but I could end up with a tail. So now it just goes back to, well, there are two things that could happen. That's the total. And how many of those are heads? Well, one. So the probability of flipping a head would be 1/2. I could turn that into a decimal, which would be 0.5. I could turn it into a percent, which would be 50%. So there is the probability of getting a head. Now, maybe I should have started this off and made it look a little better like this and said the probability of a head equals 1/2. Now my next one deals with a die. Some people say die for singular, some people say dice. Same thing. So I have all my dice here. For some reason the one's highlighted. There we go. And I want to know what's the theoretical probability of rolling a 2 on a standard die. Well, same thing. I have my sample space there. So the probability of getting a 2, well, how many are there total? I count them. There's 6. How many of them have a 2 on them? Well, just the 1. So the probability that I end up with a 2 is 1/6. Now, if I turn 1/6 into a decimal, that's going to be approximately 0.167. If I turn it into a percent, approximately 16.7%. Now, my next one is, what's the theoretical probability of drawing an ace from a standard deck of cards? Now, this one I didn't draw out the entire sample space because it was a little too big for my screen. But I did point out that there are 4 aces in the standard deck of cards. Here's the rest of my cards. And then I can think of, well, how do I calculate this probability? So I'll come back here and I'm going to go probability of getting an ace. Well, I see that there are 4 aces in the deck. Now this goes back to, do you know a little bit about a standard deck of cards? And if you do, you know that there are 52 cards in a deck. Now if I simplify this for 50 seconds, those are both divisible by 4. The 4 divided by 4 is 1. 52 divided by 4 puts us at 13. So as a fraction, my probability is 1/13. If I wanted to turn that into a decimal, that's going to be approximately 0.0, and we'll go 77 rounded. And if I turn that into a percent, that's going to be approximately 7.6%. All right, now my next one. Now in this one, I want to know the theoretical probability of drawing a red ace. So I want the probability now of a red ace. Not any ace, it has to be a red ace. So I already gave you the 2 cards that you could pull out of that deck. And if we think, well, there's still 52 cards in it. Now we have 2 of them. If I simplify that fraction, we end up, both of them are divisible by 2, so I end up with 1/26 as my probability in terms of a fraction. If I wanted to turn that into a decimal, my decimal is going to be 0.038. Percentage-wise, we're looking at approximately 3.8%. as my probability to pull one of the red aces out of my standard deck of cards. Now, this is going to be one of the little experiments that we're going to do here, and this one is going to look at, if I take 3 coins, tossing 3 coins, how many possible outcomes are there? And I said, to help us with this, we can make a sample space. So what I did is I put 2 coins up there, and we're just going to take a look at, well, what could happen? So I look at this situation and I go, well, I could get a head. So I could get a head, and a head. So there's, think of it as there were my 3 flips of that coin, or those coins. those 3 coins flipped, and I ended up with heads, heads, heads. What else could happen? Well, I could get a head, and then a head, but then on the last one, maybe I get a tail. So now I have heads, heads, tails. I keep going through this, and I could also get a head, tail, tail, or maybe when I flip my 3 coins, I end up with heads, a tail, and another head. But then I have all these other situations too where, well, maybe I end up with tails, tails, tails. That's a different situation. Maybe I ended up with tail, tail, and a head. Or I could have had a tail, a head, and a head. And then I have that other situation where it could be a tail, a head, and a tail. Now these got a little close to each other, but I really have all of these different outcomes. How many are there? Well, now I just count and I see that there are 8 different ways that I could toss 3 coins, and those are my results. So 8. Now I can use that because now it says theoretically, what is the probability for flipping all heads or no heads? And then what is theoretical probability for each? So I'm going to start off with finding calculating the probability for flipping all heads or no heads. So then I come up here and I look and go, well, where was it all heads? This situation is all heads. So there I have 1. But then I also have the situation where I have to look at no heads. Well, no heads, that would be all tails. So that would be here. There's none there. So now if I want my theoretical probability, so I go probability of, I'm going to go 3 head or 0 head. So that we could put 3 tail. Probability, remember, the grand total, which how many outcomes were there? There were 8. And in this case, I had 2 of them that came out to be all head or no head. Now, if I simplify that, I end up with 1/4. So the probability of flipping all heads or no heads would be 1/4. Now, it also wanted us, what is the theoretical probability for each? So what's the theoretical probability of 3 heads? Suppose I could have put the S at the end. So then I come back up here and go, well, where did we have 3 heads? I had that right here. And that's the only place that it happened. So then that probability would be 1/8. And then last but not least, it asks for, well, what's the probability of 0 heads? Another way to think of that is 3 tails. So I come up here and I go, well, where did that happen? Well, this was the only place that happened. So 1 outcome that way, 8 total. So I have a probability of 1/8. And then I had another problem down here. It says, what's the theoretical probability of tossing 2 heads? Okay. So now I want to know the theoretical probability of getting 2 heads. So I got to come up here into my sample space and I have to count every situation where there are 2 heads. All right. So I have, no, let's not go with that green because we've already used green. Let's go with the purple. So we have, and I've already used purple. We'll go pretty pink. We have, here's one with 2 heads. Here's one with 2 heads. Here's one with 2 heads. So I count, there's 3 of them that had 2 heads in it. 8 of them total. So the probability of 2 heads, 3 outcomes that had 2 heads in it, 8 outcomes total, my probability would be 3/8. Well, what about the probability of 1 head? Probability of 1 head. I'll do it the same way. So I'll come up here and find all the situations that have just 1 head in them. Well, I look at that and here's one. I'm starting to get a lot of things circled. Here's another one. And still here's another. So I have 3 outcomes that satisfy the 1 head. 8 outcomes total, so probability of 3/8. Now, the other probability that we talked about right away at the beginning was experimental probability. And that's an estimated probability based on the relative frequency of positive outcomes occurring during an experiment. That's a very mathy definition. Basically what that's saying to us is, if we look at all the outcomes that happened in an experiment, we just want to look at the probability of that one item happening, so the thing that you pick. And I have an example here to help us with that. So in this one it says a number cube, in other words, a die, is rolled 100 times, and a 4 is rolled 10 times. So we want to know, what is the experimental probability of rolling a 4? So in experimental probability, we just use the numbers involved. So we come up here and go, well, the probability of rolling a 4. So I look at how many times did a 4 get rolled. It was rolled 10 times. Is our favorable outcome. And then over how many times did it get rolled total? Well, that's the 100. So the probability of rolling a 4 is 10 over 100, which simplified turns out to 1/10 because they're both divisible by 10. If you wanted that as a decimal, we'd have 0.1, or as a percent, that's 10%. Now it goes on and it asks, well, what's the theoretical probability? Now that's going to be a little bit different, because now if we want the theoretical probability of rolling a 4, well, we just have to look at a standard die. How many different outcomes are there? There's 6. There's a 1, a 2, a 3, a 4, a 5, and a 6. Well, how many of those outcomes have a 4 on them? Just one of them. So the probability of rolling a 4 theoretically is 1/6, which as a decimal is going to come out to be approximately 0.167. As a percent, approximately 16.7%. So what's this tell you about the person who was rolling this die 100 times? I would say, since they only ended up with 10 out of 100 and had 10%, they weren't as lucky as what they probably should have been, because theory tells us that we should have ended up with more around 1/6 or 16.7% of the time getting that 4. Now in this one I have a spinner with 5 colors that are all equal size, so just as likely to get one as the other. And we spin it 50 times, lands on the color purple 15 times. I want to know, what is the experimental probability of spinning purple? Okay, so very similar to the last one, we're going to do experimental probability of purple. Well, how many times did purple get landed on? 15 times. How many times did we spin it? 50. So our probability of landing on purple is 15 out of 50. I notice that they're both divisible by 5, so we end up with 3 over 10, which comes out to be 0.3 or 30%. Now it asks, well, what is the theoretical probability of spinning purple? So in this one, we're going to go theoretical. So the probability of purple again. Again, we don't care about what happened in the experiment. Now we just look at, well, how many different outcomes are there? I look at my spinner and there are 5 different colors, so there's 5 outcomes possible. How many of those outcomes are purple? Come up, look at my spinner. There's only one space on that spinner that's purple, so it's 1. Now, as a decimal, that would be about 0.2, which is 20%. So in this case, I would say the person spinning the wheel got lucky, because they ended up with more purples than, in theory, what they should have. Now it says, in the last one, it says, what's the experimental probability of not spinning a purple? Now, 2 different ways to do this. I'm going to go back to that vocabulary word from another lesson called complementary events. So we already calculated the probability of getting purple, which was 1/5, or excuse me, that was the theoretical. Experimental, the probability of getting purple was 3/10. So then the probability of not getting purple has to add up to 1. Remember, because the 2 together have a sum of 1. So I'm just going to look at this as, I'm going to go with, let's go with this color. Probability of not purple. I'm going to do it like this. Remember, since they both have to add together to be 1, I'm going to start with 1, and then I'm going to subtract the probability of us getting purple in this little experiment, which was 3/10. And if I take 1 minus 3/10, I'm going to need to do a little fraction work here. Common denominator, which is going to be 10, so 1 is going to turn into 10 over 10 minus 3/10 comes out to be 7/10 would be the probability of not getting purple. Okay. And you could do it the other way as well, where you'd come up here and you'd look at it and go, well, 15 situations were purple out of a total of 50. That means that 35 were not purple. And if we did 35 over 50, we still end up with 7/10. And that's going to conclude my lesson on theoretical and experimental probabilities.